Hi, I'm Evan Drumright with Toyota Research Institute. We're not getting sound.
What are you looking for?
We're not getting sound.
Oh, sound.
It's not going through the speakers, it's coming out of here.
Let's just skip.
Okay.
Sorry, last group didn't need sound. Do you want to start
Yeah,
over?
would you please?
Toyota, and TRI in particular, has a somewhat different approach to the development of autonomous cars than many of the other developers. Most developers are focusing on the chauffeur mode of autonomous driving.
In the case of the chauffeur mode, it truly is in many ways like being on a train or a bus.
TRI's approach is actually to look at a blend of the chauffeur mode and what we call guardian angel mode. Here, you drive the car, and you continue to do so, and the autonomy is there to save you from harm. Being autonomous does not mean you have to give up the fun of driving. In fact, if you do it the right way, if you use guardian angel mode, being autonomous can actually make it more fun to drive.
So the question is, can we do enough simulation and smart enough simulation that we can bring that process of certifying an autonomous car out of the real world and into the computer? If we can, then we'll change the industry, change the world.
Okay, so that was just a quick teaser of what Toyota Research Institute is about. Of course, we've got a big effort in autonomous driving. But for those of you that don't know us, we were started with a $1 billion grant from Toyota early 2016. And since then, we've also been given $100 million in venture capital funding. Our mission is very simple. So it's to use AI to improve quality of life for all people. We have, in addition to autonomous driving, which of course is the really hot thing in the Valley, we also have programs in robotics, legged, and manipulation, and in machine learning as well. And I just want to say that we have a culture that is very focused on sustained research. We're not trying to do demo culture type environment. So I really hope you check us out. We're at tri.global, and we are very actively hiring. Thank you.
Thank you. Next speaker is Gabriel from Intuitive Surgical.
Okay. I think these may be the old slides. Yeah. Okay. Well, I'm going to talk without slides. So, Intuitive Surgical makes the Da Vinci surgical robot for robotic surgery, and let me tell you why. First of all, imagine that you're looking at a long stick with a little grabber on the back. That's the handheld that's a handheld laparoscopic surgical tool. So that's what people used before we had robots. It is a straight stick with a little grabber, and you squeeze on the back. There's no wrist, and it's actually worse. The entry point to the patient is a single position. So the surgeon's down to 4 degrees of freedom. You can imagine how cumbersome that is, and ask yourself, is that the surgeon that you want, right? So now you imagine that you're looking at the same tool, except it's got a 2-degree of freedom wrist on the end. That's what we provide. And the question is, so now you have 6-degree of freedom motion inside the body. That's great, but how do you control it? Because that little stick with the grabber on the end, that's not going to cut it for controlling that 3-degree of freedom wrist. So that's where the robot comes in. The surgeon sits at a console, has a stereo view of the robot hands inside the patient doing exactly what the surgeon's hands are doing at the console. And this makes difficult surgeries become easy, makes impossible surgeries become possible. Because of that, in the United States, Da Vinci is used in 84% of hysterectomies for malignant conditions. 86% of prostatectomies. There are over 4,000 Da Vinci robots worldwide in 64 countries, and we've actually touched the lives of over 4 million patients. So if you want to help us improve the lives in the next 4 million, please come to our booth, and we'll talk about the cool things that we're doing next. Thank you.
Hi, my name is Carlos Florenza, and I'll be talking about reverse curriculum generation for reinforcement learning. The motivation is that many robotic tasks require to reach a desired configuration from everywhere, and these tasks are quite challenging for reinforcement learning methods because their natural reward is sparse. And for tasks like trying to insert this ring down to the bottom of the peg, from most of the start states, the amount of exploration will be a lot. And hence, many practitioners try to shape the reward or give some demonstrations. But basically, with the reward shaping, the problem is that we do it by hand, and it can get to undesired behaviors. So our take is that instead of modifying the reward function, we can modify the start state distribution. The intuition is that it's easy to learn how to perform a task when you're nearby the goal, and then you can use this knowledge to learn how to do the task from further away and further away. Hence, the main question is how to automatically generate this reverse curriculum to provide the best learning signal to the policy. We focus on training from start states, which the current policy, from where the current policy reaches the goal sometimes, but not always, what we call starts of intermediate difficulty, or SOID. We bootstrap from previous SOIDs to generate new SOIDs, assuming that the nearby states are also SOIDs, and we run Brownian motion from them to take them. And here we can see that our algorithm matches the start distribution, matching the performance of the policy to provide the best learning signal. And if you want to see cool locomotion and manipulation videos, please come at the poster.
Thank you.
Hi everyone, my name is Prashant. I work with Kaushal Srinath. So as he mentioned in his talk in the morning session, our lab also works with aerial manipulation, which involves load delivery transportation. And these load delivery transportation, these systems are very highly under-actuated and has very high degree of freedom. So it's difficult to control them using Euler angles and local variables. So we use geometry control in our systems. And so in our geometry control, we use rotation matrix to represent our attitude controller. Interesting work has been done in this geometry control. Various controllers shown to exhibit global exponential stability. However, these controllers require very accurate model estimation and system parameters. In the presence of these disturbances, these controllers are shown to exhibit large tracking errors. So to avoid that, we propose a model L1 adaptive controller. We chose L1 adaptive controller because of its fast adaptation. So in our L1 controller, we have two models, one for the quadrature with disturbance and a reference model without uncertainty. We develop errors on the manifolds and then propose the adaptation law. And then using Lyapunov analysis, we show that it exhibits exponential convergence. Thank you for your time.
Hi, my name is Ayush. Today I'm going to be talking about safe bipedal navigation using control barrier functions. Control barrier function-based controllers have gained significant success in a wide variety of systems, including legged robots that we've seen in one of the talks this morning. Now, the key problem here involves safety as well as stability constraints, which are enforced through control Lyapunov and control barrier functions. And this is implemented through a quadratic program in real time. Now, in this work, we look at discrete time realizations of these functions because our navigation problem formulation is inherently discrete. We also address some of the computational challenges associated with this. Our control objectives here are to follow a desired trajectory as close as possible and to avoid static or dynamic obstacles. So we build a controller at multiple levels. At the innermost level are controllers that take into account the full nonlinear model and hybrid dynamics. At the outermost level is our barrier function-based controller that avoids obstacles and also follows trajectory. And these are some simulation results. We can avoid static or dynamic obstacles, and we can do this without having to plan footsteps explicitly. Thank you.
Hi, I'm Alex Lee, and I'll talk about how to use visual models for manipulation. Humans can accomplish very complex tasks because they have very good physical understandings of how objects in an environment will move as a consequence of their actions. So how can we use this for robots? Okay, suppose the robot sees these objects in a table, and we want to move the object from a location from where the red diamond is to the green diamond. So how can we do this? Well, we can learn a video prediction model that conditioned on the current frame and a sequence of actions, it can predict a future sequence of observations. Once you have such models, then we can say, okay, conditioned on a particular pixel location in the image, we can similarly run this through the model and predict what is the distribution of pixel locations conditioned on the given initial position pixel location and the sequence of actions. Once we have such models of distributions of pixel locations in the future, we can then optimize over sequences of actions and minimize the expected distance to a particular goal. So an example is, let's say we want to move here, and that's the resulting policy, and this would also work for goals where we
A
have
model is
multiple
able to
objects.
solve
So
the
here,
task.
we need to move the objects apart.
In this task,
All right. Hi, everyone. My name is Abhishek, and I'm here to talk about imitation from observation. So our goal is to get robots to learn things in the real world, and rewards are hard to specify. So what we're going to do is we're going to use imitation learning where we have expert demonstrations. Typically, expert demonstrations assume you have state action pairs in the embodiment of the robot, and you get these through kinesthetic teaching or teleoperation. However, humans and animals don't often learn this way. They learn by observing other people, and they observe just by visual cues. So we want to see if we can do the same kind of thing in robots, where we can just look at videos of humans or other robots performing scenes in perhaps different contexts, different viewpoints, different environments, different colors of the objects, different lighting, and so on. And we want to see if we can get robots to learn just from these cues. So to do this, we have a method which kind of looks like this, where we learn a model which learns how to translate expert behavior from one context to another. So let's say we learned how to do something in one viewpoint, we learn a model which learns how to translate it into another viewpoint. Now, given a new environment, what happens is if we translate the expert behavior into the new context, the robot can then use the translated behavior and a learned feature space to do this. All right, my time's up. Thank you.
Hi, I'm Daryl Dio from the Charm Lab at Stanford University, and so during motor control, we rely heavily on vision and proprioception to make an informed estimate of our body's configuration in space. So proprioception here refers to the sense of self, and this is the information that your brain gathers from your muscles and joints. And so in cases where there's a loss or deficit in proprioception, such as amputation here, we see reliance shift heavily towards that of vision, right? So this is visually watching your prosthesis move when you're controlling it in space because you can't really feel what it's doing. And so we set out to ask the question, in cases of limited vision, how do we provide information regarding the position of the prosthesis end effector? And so in a simplified 2D reaching case, or reaching in a plane, we propose to do this by encoding this position information haptically, and doing so via this skin deformation or skin stretch, as Mark talked about earlier, skin stretch device. So this device is able to provide tangential shear forces on the skin, and we chose the finger pad because it's very sensitive, and this shear forces you can communicate a magnitude and a direction. And so as an example, this cursor here is a stand-in for our prosthesis end effector. And as user moves this cursor towards a target, we're going to see a shear vector force on the finger pad in proportion to the position vector of the cursor. So in essence, being able to feel your cursor move on the screen. And so we ran a bunch of user studies to assess how well people are able to use this type of haptic feedback in moving to targets with this cursor when you remove vision. And my time's up and I gotta go. Come visit my poster, thanks.
Hi, I'm Laura, and I'll be talking about some work done with my co-first author, Lucia Gann, on soft robotic antennas. So we started this work with a soft-growing robot to form the antenna structure. This robot grows by everting new material in a reversible manner. The antenna itself is formed by overlapping strips of conductive material on the robot's surface. These strips extend one at a time and connect, allowing the antenna length to exactly match the soft robot length, both during extension and during retraction. We can measure the resonant frequency of our antenna using a return loss measurement. This measurement we expect for a monopole antenna will decrease as the length of our antenna increases, matching the behavior we see here. This measurement can additionally be used to form a closed-loop control on antenna frequency based off of length change. So you can see here that we are able to stably control to a desired resonant frequency by changing the length of our robot. So in the future, we believe that adding additional shape control can allow us to extend this model to more exotic types of antennas. So by branching, we can do multi-conductive paths, such as a Yagi-Uda antenna shown here. And with the pre-shaped forms or active actuation in the body of the robot, we can achieve a helical shape. So if you'd like to hear more about this work, please come see me during the poster session. Thank you.
Hi everyone, my name is Drew Sablehouse. I'm a PhD student here at UC Berkeley with Alice Agogino, and this is some work in collaboration with NASA Ames Research Center on a quadruped robot with a flexible actuated spine that we're calling Laika, the first dog in space, thanks to the funding with NASA. So what we're interested here is not necessarily on passive spines, but on spines that would actuate and help a robot maybe balance or have some other types of motion. So this is just a little brief proof of concept example where in the top with a stiff spine, the robot would fall over, but when we actuate the spine, the robot actually balances. So we've done a variety of things to justify that building a robot like this would actually help. So this is an example where one of the vertebrae of the spine actually rotates and lifts a leg. Say, for example, something like helping the robot walk over very uneven terrain. We've developed some closed-loop control algorithms for control of the spine itself. So this is by adjusting the lengths and the tensions of the cables that hold the spine together in its lattice, we can track, say, the center of mass position for each of the vertebrae. And finally, we've also been doing a little bit of a design study for examining which types of spines, which shapes of these vertebrae would actually be best for performing these kinds of bending or rotation tasks for the robot. Thanks.
Hey everyone, good afternoon. My name is Brian Serra, and like Drew, I'm from the Berkeley Emergent Space Tensegrities Research Lab. And the work I'm presenting on today is on spherical tensegrity locomotion using model predictive control and imitation learning. So tensegrity robots, to recap, are an amazing, lightweight, flexible, versatile robot that's constructed using rigid bodies that are held in a tension network of elastic elements. And tensegrity robots achieve dynamic motion by individually controlling individual cable lengths and rod lengths to have this shape-shifting behavior. But because of their coupled nonlinear dynamics and high-dimensional state and action spaces, they present a lot of interesting controls problems. And so to achieve this periodic locomotive gait, I propose using model predictive control for simultaneous actuation of 24 cables. But because model predictive control relies on solving an optimization problem iteratively in real time feedback control using MPC is pretty much intractable. With complex tensegrity structures. So to alleviate this, I use MPC as an offline expert policy to generate optimal trajectories of state and actions to train a neural network policy using imitation learning and supervised learning. So if you're interested in hearing more, please reach out to me at the poster. Thank you.
My name is Roberto Calandro. In psychology, it's well understood the importance of touch in a large number of tasks, including grasping. However, state-of-the-art robot grasping rely almost exclusively on vision. Using only vision is difficult to predict if a grasp is going to be successful or not. Touch sensing provides a direct way to observe contact forces and help discriminate successful grasps. In this work, we propose a novel approach based on deep neural network capable of learning to grasp and grasp novel objects from raw visual tactile inputs, here shown on the right side of the screen. After each grasp, our system predicts the probability of success of the current grasp, and if too low, it generates appropriate grasp correction. This process is repeated until the grasp is predicted to be stable and the object is then lifted. Our approach does not require manual engineering of features or any characterization of the sensor. We compare against a manual engineered system and against using vision only on a set of 11 previously unseen objects. Our approach achieved 94% grasp success, yielding a significant improvement compared to other baseline, while reducing by 50% the amount of force needed. Thank you.
Perfect. Hi, everyone. I'm Will. I'm presenting today on bio-inspired grippers for natural curved surface perching, and I'm working as part of the Lentink lab and the biomimetics and dexterous manipulation lab at Stanford. And our goal is to design attachment mechanisms that can attach to irregular surfaces that can vary in both surface geometry and also texture. But if we look to animals, you know, they've got this figured out, especially on trees, and even across a wide range of scales. One thing you can notice here is a lot of them use opposed gripping techniques where they grab from opposing sides of their body. So we made a simple model to get at this, and so here we have an opposed gripper on a circular rough surface. One aspect of the design we're especially interested in is the preload, so how much do you squeeze the surface before you exert the maximum external load. I won't go too much into the model here, but some basic, very intuitive takeaways are: one, it's important that the claws have a large travel in the normal direction. Two, on a relatively flat surface, if the contact point is not deep around the asperity, the shear preload will cause contact point to slip. And as you can grab farther around the asperity, your preload is dominated by the normal preload. So we made a mechanism that illustrates this concept, and if you'd like to learn more, please come to the poster. Thank you.
Hello, I'm Wilson. I'm also from the BDML at Stanford, and my poster is about the design of a spiny hand end effector to achieve human-scale robot climbing, specifically in the RoboSimian platform. So we draw our inspiration from several different sources, including past research, human climbing tools like what regular recreational climbers use, as well as biology. The underlying technology behind the design that we're focusing on right now is the idea of these linearly constrained spines, which basically sacrifice a little bit of efficiency per unit spine to instead achieve a much higher density of spines per unit area, which results in overall a much higher total potential shear stress for a given spine tile. Going up a scale, these are then integrated into a tendon-based load-sharing mechanism across the palm and phalanges of the robotic hand to ensure that one single tile does not take the entire load. And these are then integrated together into an anthropomorphic hand design, as you can see here, which seeks to emulate human-based climbing graphs such as the cramp, sloper, pinch, etc., but with the increased potential of the spine tiles. And I'm basically out of time. There's also a 3D model which seeks to predict this. Come see me if you want to talk about it later.
Good afternoon. My name is Chang Liu Liu. So non-convex optimizations arise very naturally from robot motion planning problems, for example, in human-robot collaboration and in autonomous driving. It is very critical for the robot to find feasible and safe trajectories in real time with very limited onboard computation power. And we tackle the non-convex optimization problem by convexification. That is, iteratively solve a sequence of sub-problems constrained in convex subsets of the original non-convex domain. And the sequence of the solutions will lead us to the local optima of the original problem. And our method computes the CFS algorithm computes much faster than existing non-convex optimization solvers. And our method also have good scalability and very desirable for real-time application. So this is a video showing the application of our algorithm on human-robot collaborations. And with our algorithm, the robot can generate very responsive movements to the change of the environment. So, yeah, for more detail, please come to our poster. Thank you.
Hello everyone, I'm Te Tang from UC Berkeley. My poster is about a new registration method called structure-preserved registration. So non-rigid registration have been developed for many years and to smoothly transform the source points to map to the template points. And actually, we can also use it in robotics to find the similarity between scenarios and transform paths. However, the traditional non-rigid registration usually only consider the global shape while dismiss the local structure, which will result in a local structure damaged registration result. To deal with this problem, we proposed structure-preserved registration. So basically, we introduced the manifold learning to model, to extract the local structure, and then we try to maintain it by designing a regularization term during registration. And we apply this method into the rope manipulation experiment. And during the training, we human will teach several demonstration patterns. And then during the test, our algorithm can map our current random placed shape to one of the pattern, and then try to, and also our mapping is pretty robust in terms of the large distortion and the point missing and occlusion. And this is the result. Yeah, thanks. And for more details, please drop by my poster. Yeah.
Hi, I'm Daniel, and I'm working with David Camarillo on automated positioning of oocytes in vitro fertilization. So one task embryologists have to deal with is actually positioning and orienting embryos or oocytes. And this task is very repetitive and tedious, and it's additional workload for them, so they cannot focus on more complex tasks. It's also very time critical because every minute out of the incubator might influence how the cell develops later. And one observation they made is when an oocyte is attached to a pipette and they would tap the pipette tip, that this actually causes rotation in the oocyte and reorient it. So we wanted to know if we can reproduce that. So we attached a small motor to the pipette holder to vibrate the pipette tip. And as you can see, is by only inducing vibrations on the pipette, you can actually orient the oocyte or the embryo. And then we can also apply some computer vision techniques to track features on the oocyte, like the polar body here, to know in which orientation the oocyte is and track the orientation. Thanks.
Hi, I'm Ben.
Hi, I'm Carolyn, and we're going to talk about SoftCell, a controllable impedance tactile device for active sensing.
Soft control robots enable new capabilities through active control of their mechanical properties, such as conformal sensing and large shape deformations, while ensuring safe interaction with humans through low intrinsic stiffness and mass. We're going to discuss design and fabrication of the soft cell, characterization of controllable impedance and actuation regimes, and finally, application of soft cell in a reactive control task.
We designed SoftCell to embed multimodal sensing and actuation through control of a single input, enabling capabilities such as conformal sensing, supportive loads, and exertion of positive work on the environment.
Through our controlled characterization experiments, we demonstrate programmable effective modulus and also sensing of soft cell.
We conclude with a set of task demonstrations illustrating reactive control under two sensing actuation regimes. In its passive state, the sensor can detect the slightest touch with minimal disturbance through conformal sensing. Then, the device switches to its actuation state to exert larger moments on the environment, such as in this light switch task.
Thank you to everyone involved, and come see our poster for more.
Hi, I'm Matt Model. This is joint work with Jeff Mahler, Professor Ken Goldberg, and the Berkeley Auto Lab. In this work, we develop a method for planning suction grasps by combining a novel analytic metric with deep learning techniques. Suction grasping is ubiquitous in industry due to its improved reachability, but current planning methods are simple heuristics for the most part. We propose a novel analytic metric for suction grasp that consists of two parts. First, we use a spring-based approximation of the cup's geometry to determine whether a tight seal can be formed against the target object. And then we use a novel contact wrench basis in order to analyze the grasp's ability to resist the gravitational wrench during contact. To generate training data, we sample grasp points on CAD models and integrate our analytic metric across perturbations to produce a robustness score for each grasp. Then for each grasp, we render a crop depth image centered on the grasp target. A cropped image, gripper, approach angle, and robustness score form a single training data point. We use 1,500 CAD models to generate over 2.8 million data points, which are then used to train a CNN to predict grasp robustness from a cropped, rotated depth image and an approach angle. During planning, we sample potential grasp points in a depth image and use a CNN to score each sample. The highest rated grasp is then executed. We divided 55 test objects into 3 classes based on difficulty and evaluated our method against several common heuristics in over 1,700 trials. If you'd like to see a little bit more about the results, come see my poster. Thank you.
Hello, I'm Justin Yim, and I work with Professor Ron Fearing in the Biomimetic Millisystems Lab at UC Berkeley. Our lab works on taking biological insight from biologists like our great speaker, Bob Full, and then translate those into applications on small-scale robots. Small-scale robots are really exciting because they've got a bunch of benefits like fitting into small spaces, they can be lower cost, and they're inherently very sturdy, so you can like throw them at walls or drop them off cliffs. Most excitingly today, they're also small enough to fit in my backpack, so I brought some robots with me, but unfortunately they're also small enough that you can't see them, so you should definitely come and see me at my poster. We've got a bunch of different small robotic platforms that we work on, including a series of hexapedal crawlers, a monopedal jumping robot, and small-scale actuators that can work on robots of this size. With these, we've worked on things like trying to imbue these small robots with very high performance, jumping very high or running very fast, shown on the left. We've also tried to get these robots to be able to correct things if they fall over or if they run into issues. And finally, if we have lots of small robots that are low cost, we can have many of them working in a team to overcome obstacles that a single robot wouldn't be able to overcome itself. All right, thanks very much.
Hi, I'm Jesse Levinson. I'm the co-founder and CTO of Zoox. We're building a fully autonomous fleet of ground-up electric, bidirectional, symmetrical vehicles to move people around cities. No steering wheel. I have not the ability to show you our vehicle, but I can talk about a little bit of the tech we're designing. So this is our 3D mapping pipeline. We automatically build large-scale 3D maps, removing dynamic obstacles. We also do deep semantic classification of these maps automatically and understand the whole scene. We have a simulator where we have a fully 3D environment that's accurate to within centimeters, where we can run our entire AI stack virtually. We simulate all the sensor data. So here we're simulating radar data. We have metallic surface properties, and we understand radar returns on those objects. We have a full realistic LiDAR simulator, so we understand the way LiDAR responds to different angles and surfaces. We can simulate different weather conditions like fog, which we have fairly often in San Francisco. We can do full scene semantic segmentation, classify every single pixel in the image. And this simulator allows us not only to get perfect ground truth for training data, which we mix with lots and lots of real data, it also allows us to validate corner cases. Other companies usually refer to these cartoon-like simulators when they talk about simulation, but that completely abstracts away all of sensing and perception. So we think it's really important if we're developing the software to have the full stack. We also have some really cool online algorithms like dense 3D mapping pipelines, which do dynamic raycasting and object tracking, also LiDAR semantic segmentation in real time on the GPU. This is our computer vision system we built completely from scratch at Zoox. We think it's very much state of the art, doing pedestrian, cars, traffic lights, bicyclists, and orientations all in real time, multiple cameras per GPU. We're also now driving autonomously in downtown San Francisco. So this is an example of a fully autonomous drive. You can see all the 3D agents projected into the cameras below. You can see the 3D worlds on the top left and top right. We have a very, very high degree of 360-degree situational awareness, fusing vision, radar, and LiDAR in real time. And we're really excited to put this on our own ground-up level 5 vehicle very, very soon. Here we are doing autonomous identification and overtaking of double-parked vehicles in downtown SF, which is one of the more difficult maneuvers to do. So hopefully you think this stuff is pretty cool. If you do, visit our booth out there and email us at talent@zoox.com. Thank you.
Hi, I'm back. We have slides, so in case it wasn't clear what imaginary things I was gesticulating at, now you get to see. You don't have to use your imagination. We think. Yes. Okay. So Intuitive Surgical makes the Da Vinci surgical robot. Why do we need a robot to do surgery? This is why. This is a handheld tool, and there's a little grabber on the front. There's a little squeezer on the back. This is what surgeons use if they don't have robots. It's only 4 degrees of freedom. There's no wrist. You're constrained to enter through a single point of access in the patient, and so we think we can do better. That's this. This is the instrument that we sell. It has a wrist on it. Obviously, it's very small. And so this gives you 6 degrees of freedom inside the patient. But how do you control that? Because this is not going to be that great for controlling a 3 degree of freedom wrist. So that's why we have a robot. Here's a picture. The surgeon is sitting at a console. Surgeon has a stereoscopic view of the robot hands inside the body, doing exactly what the surgeon's hands are doing in the console. And this makes difficult surgeries easy. It makes impossible surgeries possible. And like I said, because of that, 84% of hysterectomies for malignant conditions, 86%, actually, the slide's a little old, of prostatectomies in the US are done using this robot. There are over 4,000 robots in the world in 64 different countries, and we've touched the lives, like I said, of over 4 million patients. And so if you want to help us out improving the lives of the next 4 million, you should come see us at our booth. We actually have some of those instruments that you can see in real life. And that's it. Thank you.
Thank you. This was our last talk for the Spotlight session. Thank you all the speakers for being so careful with time. So we're now going to have the second break and the second poster session, and we'll come back here at 4:10 for the last session of faculty talks.